Okay. Uh, my plan for today is just take example how to solve the differential equation using Laplace. So next Tuesday, next week, there will be no class. I think I mentioned before that. So no class. We'll give you the additional video. It's a short, maybe 30 to 40 minutes video with let's say exercise for Laplace, and maybe maybe not just exercise, maybe a homework. You can wait for the announcement. If not exercise, maybe a homework that you need to submit. Okay. Now the last week we have learned that we can transform derivative of a function. So for example, if we take the f prime, and we can consider also the f double prime, at the end of the day, we can transform, like when we transform the first derivative, we get the s and then f as f0. And when we take the second derivative, we get more power, like s squared. I think it's here. S squared f of s minus s f0 minus f prime 0. And you can imagine when we have like more and more order. So actually Laplace transform is really useful to solve a more complex problem in differential equations. Now if we take the more orders, you will see the patterns. Well, let me just let me write in a new page. Okay, as a conclusions. So if we take Laplace of the f prime t, this will equal s fs minus f0, right? If we take Laplace of f double prime t, we are going to have s squared f of s minus s f0 minus f prime 0. And then we take the third order, you will see that this is going to be the pattern. S squared f0 minus s f prime 0 and then minus f double prime 0. And you could predict the next pattern. Okay, you can predict the next pattern. You will have 4 f of s and then s cubed f0 and then s squared and then f double prime and then you can have f prime, f double prime and then f cubed. So the last part of the Laplace, when we transform the derivative, the last part will be the n minus 1 of the order here. Okay. You'll see the pattern. So we can predict and make a pattern that if f prime and then f n minus 1, they are all continuous on 0 to infinity, and they are exponential order, and if the f with order n is piecewise continuous, I think we already have discussed the piecewise continuous. On same interval,
then we could write the Laplace. Let me write with different color. So Laplace of the f with order n, which means this is the supposed to be the differentials. This will equal s with power n, okay, and then fs minus s n minus 1 and f0, and then minus, let me write with another n minus 1, f prime 0, and then this minus all the way through, we have the order n minus 1 and 0. So again, the idea of the Laplace is to transform the order into a power, into a algebraic operation, into algebra. And also note that the fs is Laplace of the function. So if I want to take the process, so we are going to Laplace transform differential equations. Okay. So we have differential equations, and then we take Laplace. So take Laplace, and this will become algebraic equation. And then we can solve the algebra. So let's say solve for f of s or y s. Okay. So this is transform yt to capital Ys. So solve for Ys, and then so we get the Ys. Okay. And then the next part is we take the Laplace inverse. So we have learned also before, right? So after we get so the idea is you take Laplace, solve the algebra, and then turns back the algebra, the result of the algebra turns back to with the inverse, okay, with the Laplace inverse. So we take the Laplace inverse. So Laplace inverse, and then this will be having the solution yt of original differential equations. Okay. I think to illustrate this, well, let's say we are going to have a example. So let's say we have a differential equations, dy over dt plus 3y, and then equal to 13 sine 2t. And then maybe we take the initial conditions, that is y 0 equals 6. So at x equals 0, y is 6. So this is just a first order, and I think we could have a different method to solve this. But let's solve this through Laplace. So what we are going to do is we are going to take Laplace, so transform all these components. So take Laplace, so Laplace of the y prime, Laplace of y, and Laplace of the sine 2t. Right? We have already done all this basic Laplace, right? So So we take Laplace of all of this. So Laplace n plus 3 Laplace of y, and then 13 Laplace of sine. Okay, you can try to write directly, or you could maybe write in another notes to make sure that we have correct. For example, let me write in notes here to make sure that we have Laplace. So Laplace of the dy over dt or the y prime is as y capital of s minus, this is y of 0, right? And y of 0, we have the initial condition is 6. So we could write this as capital Y of s minus 6, right? And then the Laplace of the sine 2t, this is equal to 2 over s squared plus 2 squared is 4, right? Okay, and then we could write the Laplace of y is just capital Ys, so we could write here all the components. So s capital Y of s minus 6 plus 3 capital Y of s, and then equal 13 by 2 is 26 multiply over s squared plus 4. Take the factor out, y of s is s plus 3, and move out the 6 to the right side, so we will have 6 plus 26 over s squared plus 4. So what we are going to do now is to solve this capital Y. Okay. After we solve the capital Y, we have an equation of s. And then after that, we need to take Laplace inverse. So from the small y, go to the capital Y. Okay. Okay, so we take the capital Ys, and it means that we need to divide all with s plus 3 now. So 6 divided by s plus 3 plus 26 divided by s squared plus 4 and then s plus 3. Well, it seems that we need to solve this. We need to make sure, I think that 1 over s plus 3 we can inverse easily, right? This one, it becomes an e. But for this one, we need to separate them. Right? We can use the partial fraction. So we need to use, a lot of algebra to solve the Laplace. Or if you want, we could also, we combine first. Let's say we combine first. And you will see that we have the s plus 3 and s squared plus 4. And this will be 6x squared plus 24 plus 26. So 6 6s squared plus 50. To make it more, so we partial fraction this huge fraction now. So we take this into s plus 3 and s squared plus 4. S squared plus 4 is, we call this form is the irreducible factor, right? Which means it's not a linear. If we have a linear, then we just take the denominator as a constant a, and for the s squared plus 4, we take bs plus c. Okay, we take a linear equation on top of that. So let's solve this. Let's take the a s squared plus 4 plus bs plus c multiply with s plus 3. And this is supposed to be equal to 6s squared plus 50. And we can have a condition to make sure that, let's say let s is negative 3 to make it 0, okay, for s plus 3 to be 0, right? So we could say, so take the 3, so 3 squared is 9, 9 plus 4 is 13, so 13a is equal, so 9 is with 6 is 54, 54 and 50 becomes 104, right? And a is, what is this? Oh, it's 8. It's 8. So a is 8. And I think for b and c we need to multiply all this stuff. So let me change color. So bs squared plus cs plus 3bs plus 3c. Okay. And this one is as squared plus 4a. Okay, so s squared is a plus b, and then plus s. S is 3b plus c, and then plus 3c plus 4a. So a plus b is 6, and 3b plus c is 0. 3c plus a plus 4a is 50. I think we can get b. B is, a is 8, so b is negative 2, right? And then c is, since b is negative 2, c will be 6, right? Negative 6, yeah. So this, we have all this. Then we could rewrite the solutions. Let me write here that a is 8 over s plus 3 plus negative 2s plus 6, or 6 minus 2s to make it easy. 6 minus 2s over s squared plus 4. Okay. I think I need to make a new space. So let me copy this part. So we get the capital Y. Okay, let me just confirm, okay, what we did.
First, take Laplace for all differential equations here. Take Laplace, change to the capital YS. Okay. Well, you could write using Y or using F, depends on the question. I hope you get used to it. Okay. Sometimes we have the a small f and a capital F. Sometimes we have the small y and a capital Y. So our goal, transforming with Laplace, becoming the capital Y. And now we need to solve this capital Y. So we need to solve this equation right in terms of capital Y equal some equations. Okay. So we get this, and here, so we have this part. Okay. Now, for the 6 over s plus 3, I think it's easy to follow. But for this part, it's difficult to separate. So let's just combine first to make it a big fraction, and then separate all together. So we have a coefficient A, B, and C, as in partial fractions when you learn the calculus 1. So when we have this fraction, each fraction, we could think that, okay, each fraction can be transformed back with inverse, right? With inverse Laplace. So let's try to transform back to the small y. Okay. So let me write right here. So let me write. It's this, right? On different colors. I think it's okay. Okay, now we could see that this part here is, we can write in terms of 2 fractions. Okay, so we have 3 fractions that can be easily inverse, right? We can inverse all of this. So we take Laplace inverse. So Laplace inverse, so this become small yt, and then this will be 8 Laplace inverse of 1 over s plus 3. Okay, and then plus 3 Laplace inverse of 2 s squared plus 4 to make it into the sine and cosine, right? So this is sine, and minus 2. Oh, I forgot 2s. Have 2s. So minus 2 Laplace inverse s over s squared plus 4. Okay. So we transform back, and we get that this 8e, this is minus 3. Okay. The default is the s minus alpha, or a, right? And then plus 3, this one is sine 2t, right? And the last part is minus 2, the s is the cosine. Okay, so we get directly the results of the solutions. If you want, you could compare the result using the other method that we have learned before. If you want, okay, the first order, right? We have
the separable, we have the linear, the exact equations, and so forth, and maybe the Bernoulli or the substitutions. So imagine that we have like really high order. I think Laplace will be really helpful. Right? If we take the higher order, sometimes it has some limitations. Okay? Okay, let me give you another example here. So solve. So the key is transform, find the capital Y, solve the capital Y, and transform back using Laplace inverse. Okay, let me give you a couple of minutes just to familiarize with the system. Okay, with the system. I think you will see a lot of partial fractions. Okay, for most of the case, you're going to see a lot of partial fractions. And since we are near the end of November, well, next week at least, the last week of November, I'm thinking to determine which chapters that we are going to work on, at least the Laplace. Okay. So Laplace we will learn until there will be 2 or 3 more sections. It's including the Heaviside function, the Dirac-Delta, the convolution theorem. Yeah, I think that's most of it, the last 3. Another chapter that I would like to overcome is the matrix. Of course, not all. I believe the basic one you already have. So I will begin the matrix. Especially the eigenvalue, the eigenvector. And then the last part is the integral. If we have time, I will have the line integral and the surface integral. If not, then perhaps just line integral. But we will see. If still not really have much time, then I will cut the matrices, maybe just a really short fraction, and then just focus on the integral. Actually, the course is supposed to be like in 1 year, it's supposed to be 2 courses of engineering math. But since the curriculum for this year only having, I think, for 1, change I think you just need to take the first one only. So there will be no angular dimension 2. But I think next year maybe 2. Maybe 2. Okay, so first Laplace all of this. So the y double prime, y prime, and y. We take Laplace. So Laplace of the y double prime minus 3 Laplace of y prime plus 2 Laplace of y. And then, of course, Laplace of the e with power of negative 4t. So Laplace of y double prime, remember, the second order, so we start with s squared, and then the capital Y s, and then minus s y0, and then s is gone, then it's just y, small y, sorry, small y prime 0, and then minus 3, y prime is, let me take bracket, s, capital Y s. I hope you can distinct my capital and the small one, okay? The capital one and the small one. And then minus the small y, and then close bracket, and then plus 2 capital Y s, right? And then equal, this e with power of negative 4 is 1 over s minus minus, so s plus 4, okay? Okay, we can substitute all the conditions. So y0 is 1, so this is 1. Y prime 0 is 5, so this is 1s, or maybe let me write as just s. This is 1, right? 1. So let's just write s squared capital Y s minus s minus 5 minus 3 s y s, and then minus plus 3. And then plus 2 capital Y s, and then equal 1 over s plus 4. So we can factor out the capital Y s, and we find that this is s squared minus 3s plus 2, right? And then minus 5 plus 3, minus 5 plus 3 is minus 2. So let's move negative s and minus 2 to the right side. So we have s plus 2 plus 1 over s plus 4. Move a little bit down here. Okay, and then we take the solution for capital Y. So we divide all with the s squared minus 3s plus 2. So it takes time. And then plus this part is going to have a lot of this s plus 4 and s squared minus 3s plus 2. Okay, and then we could take the I think we can factor this part, right? This is s minus 1, s minus 2, right? Okay, so we can take the factor and we can combine these two all together. So s minus 1, s minus 2, and then s plus 4. Right, make it too long. So s plus 2 and s plus 2, s plus 4, sorry, s plus 4, s squared plus 2s plus 4, so s squared plus 6s plus 8 plus 1, right? Or plus 9, right? Okay, this is our capital Y. And the next thing is we are going to separate this big fraction into small fraction. And because all is linear factors, then we could just write with A, B, and C that we need to determine. So we take the A, multiply with s minus 2, s plus 4, plus B, multiply with s minus 1, s plus 4, plus C. This is equal to s squared plus 6s plus 9. And we could let the s, for example, we could let the s, let's say equal to 2. So this A becomes 0. So S2 is, so B, this is 1, this is 6, right? And then this will be also 0, so B. Okay, and then this equal to 4 plus 12 is 16 plus 9 is 25. I think this is the same same component as before, right? I think we've done this before. Do you remember which one? I think this one, yeah. Okay, I think I can copy all this. Yeah. Oh, I think we can copy on till done here. Yeah. Students in today's age copy paste, right? As long as you understand that's, I'm thinking that's still okay, but sometimes you just copy paste without any thinking. Okay. Okay. So this will be the results. Okay. Yeah, I think this is just maybe completion of the question itself. Okay. It's more having a context, which is the differential equation, having the initial value problem. Okay. And then you can solve it just like partial fraction as we did before, and then take the Laplace inverse, and then we can have the solutions. Okay. Yeah, I think you can copy from your notes before. This is practically similar from what we have before. Okay, let me go to just one last remarks. So if the f is piecewise continuous on the interval 0 infinity and of exponential order, then limit as s getting closer to infinity of Laplace of function of t is equal to 0. So we could start to work this Laplace from, I think, from the comparison theorem that we did before. So we take the Laplace absolute value. This is supposed to be less equal than the Laplace itself. And this is less equal if we take some value m. And we say that the f of t is the exponential order. We take e with power of a constant c and t, like that. Like I think we have done this before. And we have these expressions. We can express this after we take the integrations. We are going to have negative m, and then we have the s minus c t over s minus c. Okay. This is from 0 to infinity. Or when we put the infinity, it will become a 0. So we have m over s minus c only. Okay. So you can see that when we take the limit of this, so take the limit of s getting infinity of this m over s minus c, as the s getting infinity, then we will have the whole thing, the m over s minus c, will be getting 0, right? Because of 1 over infinity. So the Laplace of f of t, it will be getting 0. And so thus the limit of s and Laplace, this will be equal to 0. Okay, let me end the course with the introductions to the next sections, which is the translation theorems. So the translation theorem is we are going to shift our graphs, okay? Well, translate in, well, if we have the, let's say this is the, this is our capital F. Okay. What we have now, what we are going to do is we are going to shift, okay, for some A units. Okay. So this is the S axis and this is the F. So we want to shift this. Okay, consider that if we have the Laplace of f of t, that this is the Fs. Okay. And then how to translate this? Okay. How to translate this? Consider, or maybe take this multiplications with exponent with power of at and then multiply with f of t. If we take this using the Laplace definitions. Then we have, this is Laplace definitions, and this will be the multiplication of at and f of t dt. And the result is actually, we have e with power of negative s minus a d f t dt. So if you remember, our Laplace, the original Laplace, is just st. But now, when we multiply with something with exponent with power of a, we are forcing this f to be translated. Okay? So we are going to see that if we just take this s, it's our original Laplace, but we are changing s with s minus a, which means in the curve, this s will move to the right a unit. Okay, so we have f s minus a. That means that this will be f s minus a. Okay, so when we have the Laplace of e with power of a t f of t, we could transform this as Laplace of f t, but s is changing to s minus a. So for example, if we take the Laplace of e with power of 5t and then multiply with t cubed, then this is actually a translation. We shifted some function, the t cubed. We've shifted the t cubed. So this is actually Laplace of t cubed, but we shifted from s to s minus 5. Okay. So we could write Laplace of t cubed is 3 factorial, right? And then over s with power of 4. But remember, we need to shift this s to s minus a. So the result at the end, 3 factorial is 3 to 6, right? 6. And then we change the s, become s minus a with power of 4. Oh, not a, sorry. 5. This is 5, sorry. And you could also try with the same method, e with power of negative 2t cosine 4t. So this question actually means that you need to take the Laplace transform of cos 4t, and then at the end, change s to this minus 2, so s plus 2. Okay? I think that's for today's class.